Okay, so we're good. Here we go. Okay, so last time we were talking about double integrals, right? So I made a definition of double integrals, and reminder, the big idea is I wanted to rip off the idea of a Riemann sum. Keep in mind, a Riemann sum has a tremendous track record of success in single variable calculus, not because it computes area under a curve. That's incidental. Convenient geometric point of view, visual aid. It's not the point. The point is a Riemann sum allows us to chop up an interval into little pieces and consider the answer to a hard question designed on the whole interval instead as a bunch of little small questions defined on the little sub-intervals on which the questions are relatively easy. Right, that's the big point. So likewise, we figure, all right, well, let's do the analogous thing over here. Let's try to define something here, the purpose of which is not to compute volume under a surface. That's, again, incidental. That's a visual aid. It's kind of nice, I suppose. It's really not the point. It's also, and I emphasize, and likewise for single variable Riemann sums, not particularly useful in applications, right? If I can't appeal to you on, pure mathematical abstract grounds, when it comes to applications, area under a curve, volume under a graph, it's kind of a meh. It's just not that useful. So what is useful, what is really important, is to be able to take a two-dimensional region. We're starting with just a rectangle. Take that two-dimensional region, chop it up into a bunch of little bitty pieces, look at the question at hand, whatever that may be, right? Whether we're counting people in Wyoming or whether we're trying to compute the amount of water in my swimming pool, whatever it might be, answer the question on the little pieces where the question's easy. And then use the Riemann sum to add that up over all of the pieces. That's the big sort of strategy. And again, my claim is this is critical to applications, right? You want to figure out how many bacteria there are in your petri dish or whatever. We need to be able to chop up that question into little bitty pieces where the question's easy. Okay, so we did that last time, and that resulted in our definition of this thing called a double integral. And this is about where we left off last time. I think I did sneak in a comment about what the book does. They use irregular partitions and arbitrary test points, which is very important for the abstract math stuff that I'd be very interested in myself, but which y'all may not be. And the good news is that for continuous functions, that doesn't matter. It doesn't make any actual difference. And continuous functions are going to be our focus in this class, at least functions that are continuous enough. Right? And we'll worry about those details later. So in this course, we're going to ignore all the stuff about irregular partitions and arbitrary test points. You're not responsible for it. We're going to perfectly good for our purposes is this definition right here for a double integral on a rectangle. Okay, now let's see some examples of how to use this. The first one, I've already kind of trashed how irrelevant this question is, but it does make for a really nice sort of first step, foot in the door application of the idea of a double integral. And I also have an ulterior motive that I'll reveal in just a second. But let's compute the volume under a graph. So how much volume is there under a graph, namely an equation that looks like this, where you get a surface, and recall all that talk that I gave you all about graphs some time ago. So computing the volume under the graph, I am going to argue as follows. I'm going to say, look, if I were to chop up this domain down here, the region over which I want to compute the volume under the graph. If I were to take that rectangle and chop it up into little pieces, let's see here, and again, it's artistically challenging, and forgive my bad. Actually, I think that may be the best I've ever done. Just whipping it out. If you chop up that rectangle into a bunch of little pieces, notice that on each piece individually, I can talk about how much volume there is under the graph for just that one piece? Right? And that's a relatively easy question. The amount of volume under that graph, at least as an approximation, this is pretty much a little rectangular box. It's got a rectangular base. It's got basically flat vertical rectangular sides, except for a little bit of micro issues that happens near the top, right? I mean, as far as, other than a little bit of error that goes away in the limit, the volume on each piece is no problem. Height times the area of the base. Nothing to it, right? And then if you want to, from that, compute the total amount of volume, then all I have to really do is add up the answers to these easy questions over the entire rectangle. So I say the whole is the sum of the parts. By the way, notice that I am invoking some geometric intuition there, that something about the nature of this question, that the whole actually is the sum of the parts, right? And that's not to be underappreciated. So volume works that way, right? How many French fries did you get in your Biggie Fry order? Well, look at the volume of each French fry and add that up over all of the French fries, right? And having written that down, now let's look at what we have. We find ourselves with this expression right here, and this expression, sure enough, is exactly a 2-index Riemann sum. It's exactly what we were just looking at here, which means that I can rewrite it as a double integral, like so. How we doing? Everybody happy? Okay. All right. Now, I do want to point out there, again, when there's subtleties in play, you got to be careful about the subtleties. I, again, just kind of asserted the whole is the sum of the parts. We're going to be doing a lot of that in this class, being as it is a calculus class. In some sense, that's what calculus is good for, right, is addressing situations where the whole is the sum of the parts. Every application of integrals that you've seen in a single variable calculus class concerns a quantity in which the whole is the sum of the parts. Now, just to make it clear why we have to be careful about that, let me point out a question where that wouldn't be true, and where an integral, kind of like what I've done here, just would not work. Let's suppose that instead of trying to find the volume of this weird-looking shape, let's suppose that the question asks what's the surface area of that weird-looking shape. And now I'm just going to, let's just kind of think through what would it mean for the whole to be the sum of the parts. Is it true, I ask, for your consideration, rhetorically, is it true that the surface area of this shape is the sum of the surface areas of all the French fries? Absolutely not. All right, so I don't want to miscommunicate as much as I appreciate and want to get all excited about how, hey, the integrals are good for so many things, and the whole is the sum of the parts, rah, rah, right? Yeah, but well, you be careful. Make sure it actually is, right? You have to be careful about that. For terminology purposes, I like to call such quantities accumulating quantities. You're going to hear me say that a lot, especially later on in chapter 6 and 7. But volume under a graph over a rectangle accumulates over the rectangle in this sense that the whole is the sum of the parts. Surface area of that volume does not. So make sure that you only apply this strategy if the whole actually is the sum of the parts. Yeah?
Would you actually find surface area with a similar approach, though?
It'd be a very, very different question. And there's some ugly issues that we would have to deal with. We will actually do that. Well, the hard part of that question would be finding the surface area of kind of the top itself. And that is something we will be able to do. It requires some sophistication we don't have yet. But we will in a few weeks. Yeah. Okay. All right. So we've got one win under our belt. I am going to show you some others in just a moment. But I pointed out when I started this example that I have an ulterior motive to start with this example. And I want to come down to this diagram. I'll come back up to that theorem in just a second. I claim that this is kind of a roadmap of what we've done and what we're about to do. So let me just remind you kind of what the deal was. We started off by considering this part of the diagram last time. I wanted to compute in particular. First, I wanted to compute volume, and I found that you can compute volume with an iterated integral, right? But then I also made the observation that, look, I can't compute some sort of mass with an iterated integral. It doesn't make any sense. The argument, it doesn't hold water. It's just, I write stuff down that algebraically maybe looks analogous to stuff we've done in the past, but it just doesn't work, right? So don't make that mistake. Don't think that you can just, just automatically turn an application into an iterated integral. You can't. It doesn't work. Okay, so that doesn't work. This does work. Previously discussed. I've also made an argument about another thing that doesn't work. You can't immediately turn an application question into just a geometric object. I can't claim mass is volume. It isn't. This is a fundamentally different quantity, right? And that doesn't really, again, that doesn't make any sense immediately without bringing in other big guns like Riemann sums that we're about to make a reference to. Okay, so you can't do this either. Okay, and this is where we were. All right, now, what I've done now, today, well, the end of yesterday, the end of Monday, and now today, is think about this question. And we've explicitly seen now that you can compute that same volume that we've already got an answer to, right? We already know how to compute volume as an iterated integral. But now we've seen that you can also write it as a double integral, which we're not exactly sure where to go with a double integral. Why bring a double integral into it, right? We already had the way to deal with iterated integrals. Okay. I'll remind you, though, that this construction of a double integral, aka a Riemann sum, the whole point was that it's a whole is the sum of the parts construction that should apply to a vast number of applications. Any time that on a little piece of your rectangular domain, any time you can on the little piece just say, oh yeah, well, mass is mass per unit area times area, or something like that. Boom, no problem. Okay, so again, here's kind of where we are. And this allows me to dramatically emphasize why this observation here is so important. And it's not because it gives us a second means for computing volume. We already had a way to compute volume. We don't need another way to compute volume. The point is, this allows me to make the following connection. If volume is just as well computed by either double integral or iterated integral, then double integrals can be computed by iterated integrals. And check it out, I now have a path, a key path from a broad category of applications that y'all as engineers and physicists and chemists or what have you, economists, are going to have questions about, right, that you're going to need to be able to solve. And we now have a path for getting to answers. Right? So this is why this volume question was important. That volume question is important because it allows me to connect these dots. This connection itself is of momentary use only. This is what we really need. And notice now that I have this done, notice that really this all the business about volume here, this is all distraction. Right? None of this is really the point. The point is, if I want to answer an application, I can write it as a double integral. Not volume, forget volume. I can write answers to applications as double integrals. I've made a case, thank you volume, right? So, credit where credit's due. I've made a case that double integrals can be written as iterated integrals, and of course I know how to crank those out with the fundamental theorem. So we have a roadmap for answering applications. How are we doing? Is everybody with me? I know I threw a bunch of words at that. Okay. All right. By the way, so my next thing is going to be to do an actual application. I want to point out, and this is, I think, really important, and I'm going to remind you for context, this course isn't about answers. This course is about ideas, right, and arguments and reasoning. So the reasoning process that takes you from an application to an answer, that's what I'm going to be interested in, and it is critically a 3-step process. First, turning the application into a double integral. Critical observation in this point. You cannot just directly turn it into an iterated integral. As we discussed, it doesn't make any sense. The units don't match. It's nonsense. Second, to rewrite the double integral as an iterated integral. And then third, to run it into the end zone, right? And just crank out that iterated integral with the fundamental theorem, which we already know how to do. Okay, make sure to give me all 3 of these steps. Good news, it's easy. But please do make sure to give me all 3 of these steps. Okay, so for example, here are those 3 steps. Let's see, what were my colors? Green, blue, orange. Okay, step 1 in this application question. I want to compute the amount of mass distributed over a rectangular area where density varies, right? Density is a function of position. I mean, this is not a single variable calculus problem. There's no single variable approach to this because the density depends on both variables. You can't, you can't slice this up in one direction and start doing business. It doesn't work. But I can make an argument that mass is a double integral of density. Now let's break that down real quick into the details. Mass is an accumulating quantity. The whole is the sum of the parts. On each little piece, mass is density times area. That's what mass per unit area is. It's the thing you multiply by area to get mass. Right? So that's an immediate, no problem. And then by definition, this is what a double integral is. So step 1 is to rewrite mass as a double integral. Everybody on board with that? Now I fleshed this out in gory detail here to break it down into all the steps that are necessary. Notice though, you're eventually going to be turning a Riemann sum into a double integral, and this Riemann sum notation into that integral notation, and ultimately that's all these things are. Right? This is just notation, shorthanding what a Riemann sum is. So if the notation is convenient at the end, most people are pretty comfortable kind of, using that same notational shorthand kind of all the way along. And it just makes it a little bit easier to write things down. It is always understood when you write down an integral that you're talking about a Riemann sum. That's implicit. And so in practice, mass, the whole is the sum of the parts, on each piece of which the question is easy. And, of course, dx dy is area, and that's a double integral over a rectangle. So in practice, this is what people write down. It's fine. Everybody okay? Okay. Step 2. Double integrals and iterated integral. And that's an easy one. You just write it down. And we've already showed that. And by the way, here's the theorem that I kind of skipped over and forgot to go back to. This step 2, showing that a double integral is an iterated integral, is, again, what we showed by computing volume 2 different ways. Okay, so you just write it down. Nothing to it. And then step 3 is to crank it out. And again, now we've already done this. Y'all know how to compute iterated integrals. You do them inside out. That inside expression, the inside integral, is a single variable calculus problem. Don't forget that the outside variable is a constant for the inside integral. And then that leaves you with the outside integral, which is literally a single variable calculus problem. So that's all easy punch up. Okay. Does everybody see the three-step process there? Okay, now this again, all expanded for maximum, visibility of every little micro step. Now let me show you in practice, day in and day out. What do I expect y'all to do in Math219? And I wrote more than is really necessary here. In practice, it's perfectly reasonable just to say mass is a double integral of mass per unit area, which is an iterated integral, which you can then compute with the fundamental theorem of calculus. Is that good? Okay. Again, resist this temptation. So many students want to bypass and just do directly this. Why should I have to write this down? Their inner monologue tells them. It's perfectly obvious that that's where that came from. The problem is, again, if you write an application question immediately as an iterated integral, what you're doing is you're making a claim that you can make an argument like that. And that's a bad argument. It doesn't hold water. Okay, let me, in practice, practical point, outside of Math219. In a context or a course where it's expected and assumed that you're proficient with multivariable calculus, yeah, okay. In those contexts, yeah, sure. Everyone knows that you know, right? If I'm talking with one of my colleagues about how to, if I want to make an argument, I want to say mass, and I want to compute it as quickly as possible, yeah, I'd probably just go ahead and write that down. But this is a course of multivariable calculus in which you can't assume that it'll be understood that you already understand multivariable calculus. That's what the course is, right? So in this context, I do need to disallow that. I need you to doff the cap to the importance of the double integral in this argument. And then, of course, you're going to have to write out the iterated integral just for kind of mechanical purposes to then get to the answer. Everybody with me? Okay, cool. Oh, yeah. Mm-hmm.
Just a question. If it's not a rectangle and it's like...
Yeah, that's a huge topic. We're going to be getting to that in just a couple minutes. Yeah, and a long conversation ensues. Yeah, absolutely. Okay. All right, so I've showed you how this double integral notation is a convenient shorthand. I just want to show you another example where the double integral notation is particularly convenient, and this kind of stuff comes up quite a bit, actually, in practice. So the question we have here is a work problem, and let's imagine we're building a wall. The idea is that the wall is going to be understood by this rectangle. And you'll notice that I have everything referred to in terms of x and y coordinates that I've set up in a particular way, as indicated here. So y is up. This being a wall, the top is high up there. And if you think about it, it takes a lot of work to pick up the big, stones or bricks or whatever they may be that are building up the top of the wall. But it takes a lot less work to pick up off the ground the bricks that are only going up to here, or stones or whatever. Okay, so altogether, over this entire wall, what's the grand total amount of work that it takes to just the picking up of the stones? This is not to mention all of the other details that go into making something, right? Just the picking up of the materials. Okay, so here's the idea. That's a hard question. But the whole is the sum of the parts, I claim. Right? The grand total amount of work is the sum over all of the bricks of the amount of work that it takes to lift each brick. Yeah? Cool. Okay. Well, on each brick, the question's relatively easy. And here's where the integral notation's gonna come up. How much work does it take to lift this one particular brick? Oh, well, that's just how much does it weigh right? A DF, a differential amount of force. There's a differential amount of sort of weight of that brick times how high do I have to lift it? And well, whatever its location is, x comma y tells me how high I have to lift it above the ground. Yeah? Okay. Let's see here. How much does that brick weigh anyway? How much does the brick weigh? Well, whatever, mass per unit area, right? Now I'm going to have to know that, what this mass per unit area is. This is going to have to be given. Notice that it is, right? So this brick is, this wall has some sort of an asymmetry to it where for whatever weird reason it gets thicker as you go further over to the top right. I just made up this function, by the way. This isn't sort of, I would never suggest that you build a wall like this. That would be weird, right? But just just to have something to write down. Point is, whatever that function is, we need to know what that is because weight per unit area times area is how I understand weight. Okay. And then let's see here. Check it out. With my integral notation, I now have a double integral. I now have an expression where I'm adding up over all the rectangles and where the right-hand side is the area of the little pieces. And keep in mind, that's what a Riemann sum is. You come back to this, our original strategy. Why do we want to chop up rectangles? It's because I'm interested in questions where on each little piece, the answer to the question I'm looking for is something times area. And we now have that in this application. Is everybody cool? All right. It's all over. It's all over but the shouting. We have a double integral. I can make the easy claim that a double integral is computed with an iterated integral. That's the exact same thing. I plugged in some stuff, right? I plugged in that density is this function 1 plus x plus y. But other than rewriting, I have turned a double integral into an iterated integral. And then lastly, the plug and chug, how to compute an iterated integral. And let's see here, I guess there was, anyway, so there's your answer. And that's details that make sure that you can follow through even more. Make sure that you can do this. Again, reminder, there's a couple of little detail devils, right, when it comes to actually cranking out an iterated integral. Make sure you realize at every stage in the process what variable is playing what role and treat it appropriately. Yeah.
So is that iterated integral just the double integral with bounds? Or what else would be the difference between them?
The difference is that they are structurally different things. A double integral is where I take a rectangle and chop it up into sub-rectangles, which you would never hear in a single variable calculus class, right? An iterated integral is a single variable integral with a single variable integral inside of it, right? So now, look, aesthetically, yeah, I get it. Aesthetically, you see these two integral symbols and you see these two integral symbols, and it's like, come on, it's the same thing. But they're really not, right? Now, this similarity is the motivation for why people like this notate. It's like, okay, I know where I'm going with this, right? I am going to be able to cite a theorem that this algebraic structure is the same as this, is numerically equal to this algebraic structure. So the notation is convenient, but it's also deceptive. And these are structurally very different things. Does that make sense?
Yeah.
Yeah. Great question. A lot of students get confused on that. Yeah. Okay. All right. Okay. So, to your question, I believe, what do we do if the domain's not a rectangle, and how does that change things? And good news, bad news. Good news is it doesn't change it very much. It really doesn't. Bad news is there is a difference that is going to make things harder in practice. But anyway, let's go through the process if the domain's not a rectangle, and let's go back to the volume question, just so again, it is a nice visual aid to think about volumes when we're doing this kind of thing. So let's compute this volume. This is you'll notice the volume under a graph sitting over, no, wait a second. Now this time sitting over a different shape that is not a rectangle. But it's still a volume. It's still a volume under a graph. I could still need to know how much volume that is. How would I do it? Well, I would slice it into pieces. Right? This loaf of bread, misformed loaf of bread, the total amount of bread is the sum of how much bread there is in each slice of bread. Right? I can still look at that individual slice of bread. Let's see here. Look at this slice of bread. Right? And I can still say that slice of bread has volume, which is area times thickness. The area is still the area under a curve, which I can compute with, again, another integral. I mean, it's really just like the previous question that we've already got an answer to. And you can see that playing out in how this is written down. So what is the difference? There's very little. It's really just kind of one thing. Let's see if I can, here we go. The main difference is that if you look at the inner bounds, so let's think about a particular slice here. We're looking at, let's say, here. On that slice, right, as we try to compute that area with an integral, the inside integral, this lower bound here comes from, well, wherever it is on this picture that I need to be starting in the x direction. And I'm just going to make the observation that, well, this lower bound, now it depends on your y. Right? For certain values of y, I get a lower bound, let's say, over here. But you could imagine that for a different value of y, like if I were, my picture is going to get in my own way. If I were looking at this value of y there, then I'd be looking over to a different point as the starting point for the slicing process, which would give me a different starting value for x. Ultimately, I get a different starting value for x. I get a different lower bound for my x integral because this edge is curved. So that's the only difference. Having curved edges just means that you're going to have functions as your inner bounds. That's it. A bunch of details and examples to follow, but does everybody see the big picture? All right. Likewise, the upper bound, of course. Okay. So, now, wow, what a hard picture to draw. By the way, it was hard, trust me, drawing that picture, having it look decent. Am I going to have to draw a picture like that every single time we want to do a non-rectangular? Oh, my gosh, and what if I'm not computing volume? Right? What if I'm computing something other than volume? I can't really draw the picture. That gets weird. Some key observations to make. How does verticality, right, the three-dimensional part of this picture, the vertical part of this picture, how does that manifest in the result? Well, look, it's just telling me what z is. Right? What is z? Z is the value of the function. It's just going to tell me what my integrand is. That's it. That's the only way anything vertical in this picture shows up in the result. So, good news. I don't even really need to draw that because I should already know what my integrand is. My integrand, if I'm going to write down an iterated integral, my integrand is the same as the integrand from my double integral. So notice this, right? The iterated integral, the double integral, same integrand. So if I've already made a case that, mass is a double integral of density, or population is a double integral of population density, whatever it is, I know my integrand. I don't need help from a picture to decide what my integrand is. all I really need to know as I try to turn a double integral into an iterated integral, all I really need help with is figuring out what the bounds are. That's it, just the bounds. And so back to this picture, what contributes to understanding the bounds? Well, the bounds all come from looking at the domain. Right? The lower bounds, let's see here. The outer bounds are just sort of the endpoints, if you will, of the thing as I slice in that direction. It's entirely from the domain. Height's got nothing to do with it. And the inner bounds, as we just discussed, kind of come from the shape of these curves. And yes, there's a bunch of details, and we're going to see a bazillion examples of how to use those curves to get these inner bounds. But that's it. The bounds come from the domain itself. So you don't need to draw this hard three-dimensional picture and slices, hard to draw slices of this hard to draw three-dimensional picture. Just draw the domain. The domain itself much easier to look at. And so then notice that once you've, whoopsie, get into this mode here. Once you've drawn the domain like that, well, you can see the y bounds there and there. And then for any given value of y between those y bounds, your x bounds are going to go from there to there. And how do I know what are these? How do I, in practice, how do I determine what these functions are? Just we're going to look at the picture and kind of connect the dots as needed from the picture as follows. For example, this lower bound here, notice it comes from that point. That point decides what that lower bound is. That point, of course, is on this curve. That curve is going to have some equation. And within that equation, what am I solving for? Well, I'm solving for x. Because that lower bound I'm interested in is a value of x. So this is our connect the dots process that'll help me find my lower bounds. To understand a given bound, identify what point it corresponds to. Identify what curve that's on. Identify what equation describes that curve. And then in that equation, solve for the variable in question, in this case x, and that tells you your bound. Yep.
So this would only apply if your top and bottom line are like straight, right?
Well, we're going to see a bunch of examples. I mean, it's going to turn out that, kind of yes, but they also could be straight in the same sense that if this were to kind of come up like that and not really have a top edge, but if it just kind of rounds off, then that'll manifest by the upper and lower x bounds just being the same number.
Okay.
Yeah. So I drew them as separated in this case just for kind of visual purposes. In practice, it might work out this way, but it doesn't really have to. Yeah, yes.
Does this symmetry matter in this case?
No. Again, that was just artistic weakness on my part. Yeah. Right. This could be weird and squiggly, and this can be smooth and graceful like this. Yeah. Totally. Okay. Let me just dive in and show you some examples. You'll get the hang of it from the examples. So here we have a triangle, certain vertices given. We want to compute a double integral. Now, I want to emphasize one thing. Notice I have not phrased this as compute the answer to an application. I'm going to assume that we've got a double integral given. Let me go back to our roadmap. Let's see. Yeah, here we go. In our roadmap here, what we're focusing on right now is just this. How to turn a double integral into an iterated integral. Yes, there's always the question of, hey, where does this double integral come from? Maybe, am I computing mass or work or whatever? The Let's assume that part's been done, either because it's been done for me or because we've already done it, whatever. I'm also, when we're done, I'm not going to actually crank out the answer. That, again, is something that I know y'all know how to do. I just want to talk about how to make this transition. So, phase 2 only. Here we go. Okay. So let's do it. Arbitrarily, I'm going to use this order of slicing. No particular reason. We're going to do it the other way in just a moment. But let's start with this way first. I need to know my x bounds first. So in other words, as I go like this, where does x start? Where does x end? That's pretty clear from the picture. Right? This lower bound for x, it comes from that point where x is clearly 0. And the upper bound comes from, well, this whole line, for all of which x is equal to 1. All right? And if you prefer, you can just, pick. It doesn't matter. I could pick this point or I could pick that point. It doesn't matter. They all have the same value of x. Okay, so x goes from 0 to 1. Now, we're going to fix x. Looking only at one slice now. On that single x slice, I now want to know what's the range of values of y. Right? Y starts where, y ends where. Okay, so y starts at that point, which is on that curve, which has that equation. Right? I'm following my process, right? My bound is determined by a point. My point is on a curve that I identify from the picture. The curve has an equation, and now, last step in that process, I need to solve. Don't forget what we're solving for. I need to solve for y. So in this equation, I solve for y. Well, that was easy. It's already solved for. You get lucky sometimes, right? And having solved for y, this then is my lower bound for the y integral. How are we doing? Pretty good. Okay, let's do the upper bound for the y integral. The upper bound comes from this point. Again, thank you, picture. That point's on this curve. Thank you, picture. It's really important to have a good picture. You really need the picture, right, to be able to make these conclusions. Well, which curve am I looking at? Right? That curve has this equation. Now you got to look at the givens, the certain points, and so this curve is defined by 2 key points and algebra 2 and all that, right? You can find the equation of that line. It'll be different in every question. But it has that equation. Keep in mind now, what am I doing here? I'm trying to find y bounds, right? I'm interested in solving for y. So solve this equation for y. The thing that you get when you solve for y is your upper bound. Everybody see the process? Now, those of you who have had a high school course in multivariable calculus may have seen a quicker and kind of looser treatment of this. That the quick and loose treatment that is very often done in high school courses works sometimes. And it absolutely falls on its face. Catastrophe of failure also sometimes. Right? So that's why I'm emphasizing this process. You need to identify what is the relevant point. You need to identify what curve or geometric object is that on, what is the equation, and then solve for what you need. It's not enough to just kind of, you just kind of look at the equations and just kind of pick part of it out and stick it on there. That's not valid reasoning. Okay. All right, now I did arbitrarily, completely rabbit out of a hat, decide to do my slicing in that order. Just as an exercise, let's do it now in the other order. dx dy instead of dy dx that we just did. All right. Well, same process though. Y bounds. Well, here's my first Y slice where Y is clearly 0. Here's a bunch of intermediate Y slices. Then there's my last Y slice, which is 1. Again, sometimes the picture just is clear from looking at it. But sometimes, depending on the situation, like let's take this upper bound here, you might actually have to do some algebra, look at the equations of these two curves, find that intersection point. You all know how to do that kind of algebra, of course, and solve to get what that y is. But again, sometimes it's just given in the picture, as in this case. Okay, outside bounds, usually pretty straightforward. So now we're going to assume a certain value of y, our outside variable. Now we're going to ask what is the range for x. Right there. Right? What's our x bounds? And, well, the lower bound is going to come from that point, which is on that curve. Thank you, picture. Got to have a picture. Right? That curve has this equation. Wait a minute, what am I doing here? I'm solving for an x bound. So in this equation, I need to solve for x. And that means that my x bound is y. Right? Now again, notice I did the process. Right? Okay, let's see here. My upper bound is going to come from that point, which is on that curve, which has this equation. Wait a minute, what am I doing here? I'm trying to find an x bound, so I need in this equation to solve for x. And whatever I get is my upper bound. Everybody good? Yes?
I'm struggling to understand why you kind of like choose, not like choose the bound up like arbitrarily, but why you don't just go from like 0 to 1 for the x bounds as well.
Yeah, no, I totally get that. That is a common source of confusion. Let me just point out what that would mean. So keep in mind we're adding up. I mean, just as a geometric sort of convenience, I'm adding up a bunch of volumes. I need to compute these cross-sectional areas, and those areas have to correspond to the actual loaf of bread that we're slicing up. Right? Okay, well, so these inner bounds tell you for a given outer variable, they tell you where your slice of bread starts and stops. So key word, for a given value of y, for a given value of your outside variable. Right? So if I were to say, hey, for every value of y, if I were to put a 0 here, let's see, how would I, give me a second. If I were to put a 0 there and claim that my lower bound is always 0, that would suggest that I don't have this shape. That would suggest that I have this shape for my lower bound. That would suggest that I'm adding up over a rectangle, which I'm not. Does that make sense? Yeah. Now, let me address a different sort of point of view on this. A lot of people say, but the lowest value for x is 0. And it is. But that's not what this is supposed to be telling me. That's not supposed to be telling me the absolute lowest value of x. That's supposed to be telling me the lowest value of x for a given value of y. For a given value of y. And on this y slice, we don't get to x equals 0. Now don't worry about it. We'll account for that 0. This point over here where x is 0, we'll get to that when y is 0. Right? But that's not what lower bounds are.
Yeah. That slice is completely arbitrary. It doesn't matter what.
Yeah, it has to be arbitrary. Yeah, because I need to know about these slices as they vary, as for different values of that outside variable. Yeah. Okay. All right, and we are out of time. Amazingly. Okay, so we'll draw the line right here. Next time I'm going to show you various kind of tips and tricks about how to make good decisions on this sort of thing. Y'all have a good one. See you on Friday.